Okay, perfect. So today, as we said, it's in two parts. The first part is a bit technical, and it's about an evolution of what we said last time on multi-agents. I hope it's not going to be too much trouble to follow. And the second part, we will see something which is a bit of exploratory in the sense that we give you a few resources to go out and play with yourself with some state-of-the-art reinforcement learning with some nice environments. So the first part is this multi-agents in matrix games. So the idea is that so far we've seen now an agent can react to an environment, and everything that happens in the environment can be stochastic, can be deterministic, but it's not playing against the agent. So it's not trying to react to the agent's policies. But this is not the case in most situations. In most situations, we have many different agents, and each agent is trying to do different things, and they are trying to respond to their each policy. So multi-agents it's a very important, interesting branch of reinforcement learning, but it's clearly very hard. It's still a major research topic today. And one of the simplest part, which is still not trivial at all, is that of agents in what are called matrix games. So matrix games are very similar to multi-armed bandit. They can also be called adversarial bandit in the sense that there is just one state. You never move away from your state. So transition probability or always keeps you in the same state. And there are multiple choices of action. This is the only thing that you have as an agent to decide what action to do. But the problem is that the payoff, so the reward, which is going to be called payoff, depends on what the other agent is doing. So it's not like you're pulling lever and whatever you do, it's always the same. You're pulling lever, but depending on what lever the other agent pulls, then your reward can be different. And this can be generalized to n players and multiple actions. We will try to see what happens in the simplest case, which is 2 players and 2 actions. So at each time, both the players will decide what to do, either one action or the other, and they simultaneously choose their action without knowing what the other is going to do. Okay, they can know the past, of course, but they have not access to the immediate action the other is going to do. Then the payoff is a function of both actions. And since we are dealing in a 2x2 system, 2 players, 2 actions, then we can describe the payoff in 2x2 matrices. So for player 1, this is the payoff matrix. It means that if player 1 is doing action 1 and player 2 is doing action 1, then we are here. So the payoff for the player 1 is this one here. If player 1 is doing action 1 and player 2 is doing action 2, then this is the payoff for player 1, and so on and so forth. Player 2 has a different payoff matrix, can be completely different, can be the same, can be symmetric, but I mean, in general, it can be completely different. And so the reward for player 2, again, if player 1 is with action 1, player 2 acts with action 1, then player 2 has this reward here, and so on and so forth. We can also, generally, if you look for matrix games online in the conventional, one of the conventional form, it's also written like this. So you will have numbers with the comma, and it means just that this is the reward for the first player, this is the reward for the second player, or payoff. So you have only 2 actions, then your policies are perfectly defined each by one number. For example, the first player here has a policy, which is, of course, the probability of doing action 1. So we will call the policy for player 1 of doing action 1. which is a number between 0 and 1. And then we have the policy for player 1 to do action 2, which is none other than 1 minus the probability of doing action 1. Okay, and so this is for the second player. And of course, you can clearly see that, I mean, with two numbers, we have perfectly defined the state of the policy space. Okay, the expected payoff. So when I fix these two numbers, what is the expected payoff that the two players can see? Of course, it's for player 1. You have to sum over all possible couples, a couple of actions, and then it's the probability of player 1 to do one action, the probability of the player 2 to do another action, and then the payoff for those two combined pair of actions. And of course, the player 2 has the same identical thing, but instead of getting the payoff related to player 1, has the payoff related to player 2. Okay, so this is the problem we are. Of course, now what reinforcement learning wants to do, it wants to try to maximize this expected payoff. So both agents will try to reach the highest possible number of G in some way. Now, you can already see that the problem is it's different from that we have tried so far, tried to find so far. Before we had the idea of optimal policy, which was a optimal policy in which you have to follow to get the highest possible payoff. But then now what you do and what you want to optimize depends on what the other is doing. So if you're playing with an agent which is simultaneously trying to optimize his expected reward, it's very different when you are playing with a different agent which you already know that he always does the same thing. So it's not even that clear to what optimal policies are, in the sense that in game theory we have a concept of stabilities of strategies, and so it's a rather different problem, and it's rather different. It needs a rather different also way of discussing it. But now we are going to deal with it in a simple way with reinforcement learning, which it's not all the story, it's just one way of seeing it. Okay, so also I said that there is no simple answer to the question of what the optimal policies are. Clearly, this depends on the game. So there are games which are very trivial. Okay? If I have a game which says that if both players do action 1, you get a very high reward, and everything, any other choice, it's a very bad case for both, then the optimal policy is very well defined. It's simple. It's for them both to do the good thing. But this is not the most interesting case, of course. And the most interesting case is when the two agents have conflicting aims. Okay, an important class of this is the so-called zero-sum reward games. The zero-sum reward games means that if one player gets to get a positive reward, then the other player gets to have gets a negative reward, so that the sum of the two is equal to 0, whatever happens. Okay, this is the most adversarial case possible. Okay? If you are trying to maximize your reward, and in the same way you're in a sense trying to minimize his reward, the other reward. So this example is a simple example which I have seen in theory class also, which is called matching pennies. So you have two agents, they all have a penny, they can show the other head or tail, and player 1 wants, so player 1 has a positive reward if he plays head and the other play head, or he plays tail and the other play tail. So player 1 wants to match the other coin from the other player. Okay, and this is because the diagonal terms means that both actions do the same. Both players do the same action, so both show heads or tails, and the off diagonal means that they are doing opposite actions. Player 2 wants to do that. Player 2 does not want to play the same action as player one. So it does not want to show the same flip of the same side of a coin, but they want to show an opposite one. So clearly, this is very simple game. This is just two players, two actions, but then the agents are trying to do completely different things. Okay, so how can we? What is the solution, or what is the answer from reinforcement learning to this kind of games? So one possible way to approach the problem is to have two different independent reinforcement learning agents, and they play against each other, and they learn from their experience playing against each other. So they both update their policies using a policy gradient method. And in particular, they're using exactly what we discussed last time, which is the natural gradient softmax policies algorithm, which we used last time. Okay, just a brief recall. This means that each player, since they have only two actions, they actually can have only, they have two parameters in a sense, but it's like they have only one, because of course they are one probability is one minus the other. And essentially the probability of doing an action is an exponential of this parameter divided by the sum of the exponential, so that the sum it's one. Okay, so our tackle to this problem of a 2x2 matrix of agents which are trying to maximize their own reward is this. We take two different agents, and both of them learn independently, and both of them learn with a natural gradient algorithm. Why do we do that? Because this particular choice of way of doing multi-agent reinforcement learning for this kind of games, we will see it's equivalent to something which has already been known in evolutionary game theory, in ecology, and it has a direct comparison with something which is done in evolution of population. Okay, so this is one possible way of dealing with reinforcement learning. So why I say that this is equivalent to something already known in evolutionary game theory. The reason is that, as you see in lecture 18, this way of dealing with two independent agents with natural gradient makes so that the gradient of expected payoff, so this is the payoff for player one, and what we need in the natural gradient algorithm is to go up this term here, and this term here, so the gradient with respect to the parameters which changes the policy of the expected payoff is this term here. This term here is exactly the payoff that the player expects to get if he plays action A and the player 2 plays his strategy. Okay, so I have player 1. This is the expected payoff of player 1, which we define like here, which is very simple. It's just all the different possibilities of actions with their probabilities and the reward. And the change of the expected payoff for player 1 of an action A, so either 1 or 2, is just how well this action performs against the other opponent. Okay, so this is a very simple idea. I have two actions. The other player is going to play a strategy. I see how well these two actions perform. And it turns out that the action with the highest payoff, so the one which performed better, gets exponentially more probable in the next step. Okay, so this can have a nice interesting feature, because you play two actions, you see what happens. One gets more probable, but also the other agent have seen what you're going to do. So actually, the two actions will change, and since they change in time, then also what was the best action to do before can change and become the other one. So, but at each time, the action which performs better is growing in probability in an exponential sense. Okay, this is what happens if you have a natural gradient, two independent agents, and try to match them other in a matrix game. Instant by instant, the agent measures how well one action performed in respect to another, and on average, the instantaneous change of probability 1 or 2 depends on how well they performed. Okay, and this application of natural gradient algorithms for adversarial bindings is called XP3, which means 3 times exp, exponential weight, because we are using softmax policy, exploration, and exploitation. Okay, and it's very well known in the literature. You can find a lot of papers also which have been concerned about the convergence. I mean, it's a case study, very well studied. But the point is that we can do it numerically now. It's very easy. So this is the usual, exactly like the last time. It's the algorithm with a natural gradient. It's an actor critic. So you remember it has 2 things. It's one, it needs to store the approximation, the values. Okay. But in this case, it's not even true because we have only one state. So this actually, it's just, we don't even care, but in general, it's something which we use. But this is the only thing that it matters here in this case, because we have only one state, but we have possible choices. And here you store the policy parameterization. So, but this is the same code we used last time for the natural gradient. It's an actor critic. Then the single step update we saw is just this one, which was the update for a natural gradient. Okay, this was exactly the same as before. I added one thing because I think it's nice. I added this line here, which gives the starting probability. So right before, starting probability did not matter in the sense that we want to find an optimal policy, and we hoped that whatever was the starting probability at the end, at the starting policy, let's say, at the end, we all converged to the optimal policy. Okay. If I started with a policy which was very far, maybe it took me longer, but our hope and our convergence and assurance in the case we were inside some classes of algorithm was that at the end we were in the one and only optimal policy. But now it's a different fact, because now this starting probability determines the first moment these 2 agents, what they are doing. Okay, and we will see that this can have a very striking different result on what happens. So okay, what happens? So this is the nice thing. So we have again, we have now, look that we have a very large number of episodes. Gamma is useless because we are in one state, so we don't actually care. Okay, we initialize the parameters again, but the important thing is this: we have the payoff matrices, which are the, apologize, I changed them. We go back. Okay, payoff matrix for player 1 is he want to match pennies or actions, and payoff matrix for player 2, he wants to be doing the opposite thing as player 1. And now we can play around with the probabilities to start from one another. Okay, so we can. So let's do, for example, let's do this and they first try and see what happens if they start from a very, very, very different position. So the first player at the beginning plays almost always tail, and the second player at the beginning plays almost always head. Okay, so we can go, and then this is the usual run over the episodes. The state, there is only one state, so I just define an empty state, state 0. Then the two get their actions simultaneously. They do not know about the other, and they get the reward, and then there is this single update. This is the standard thing. Okay, so it will take a while, but fortunately I already made some plots. So let me go here. Let's see. I have to apologize. Now your faces are covering my terminal window. Okay, perfect. Let's do this. Let me. Okay, so this is what happens. Can you see? I hope so. We started from here, right? 0.85, 0.85, or perhaps somewhere else. But it's not relevant. The problem is that what happens if we are here, for example? Let's say we are here. This means that this is the probability of a player 1 to do head. This is the probability of player 2 to do head. Okay, so we are here, and both of them are playing head. So player 1 is very happy because, I mean, he's playing head, the other one is playing head, so he said, okay, this is super fine. But then what happens? It happens that player 2, then he finds out that perhaps this is the other way around. Yeah, I guess it's the other way around, unfortunately. But so the labels may be wrong, but we will see. The point is that if both are playing the same, player 2, which is the one who wants to play different one, say, okay, now I've seen that he plays a lot head, then I want to play the other one. Okay, so what happens that in the probability space, since both are playing the same, I'll say, okay, I will diminish my probability of playing the same as he, and so it will, the probability of doing the action will change, and one of those will diminish. The one who wants to play differently will diminish, and they will arrive to a quarter here, where now it's the probability of doing the two actions, they are rather different. So one player will play with a very high probability one action, and the other player will play with a high probability the other action. So here, the player who wants to play unmatched pennies is very happy. So he's very content of the situation. But of course, the other says, okay, he's playing a lot of tails. I don't want to play head anymore because I want to play matching. So he changes his policies again, and he changes his policy to play as many tails as possible. Then they are playing, both are almost never playing heads, so they are both playing tails all the time. So what happens? It happens then the player who wants to play matching pennies is very happy, but the other one is saying, okay, I know that he's playing a lot of heads, I should play a lot of tails. And then again and again and again, okay? So it's the dynamics of the policies are such that if you start from a position in which both the two are playing very skewed actions, then what happens is that they are going round and round, and they will always go around and around, playing always skewed action, but changing along these trajectories. And this is the first time we've seen it. Then what happens if, so for example, I'm playing, I'm starting with different actions. So I'm starting with a different initial probability condition. So for example, here I'm much closer to 0.05, but they're still not 0.05. And you can see that, again, they are going round and round. So this is a proper dynamics of the policies. The starting probabilities matter because then their evolution, it follows a circular motion against the center. The center is actually the only part which is stable, because if you're playing half and half, then it's actually stable because the other one has no incentive to play differently. So it stays around here. Okay, so this is what happens with reinforcement learning natural gradient with this kind of solution. I have two agents, they changes their behavior depending on the other one, and what can happen, like in this case, that they circle one around the other forever, changing the policies because they are reacting to the instantaneous policy of the other, but also the other is reacting to the instantaneous policy of the first one. Okay, why I said that this was a nice case, because this is something that you may have already seen in other courses, and generally it's an evolutionary problem, and which is a very simple model of growth and changes of population, which is called replicator dynamics. And this solution of different agent learning with natural gradient is actually what is it's equivalent to this very simple model of growth called replicator dynamics, which is not based on learning, it's based on fitness. Okay, so replicator dynamics, what it is? It's a mathematical model of growth, which is used to study how population change in size relative one on the other when they have different fitnesses. So in replicator dynamics, for example, I have a population made of different types, n types, and each of this type has two scores. One is called a fitness. It's how good they are in their environment. For example, how well they manage to get food, how well they manage to survive diseases and everything else. And this is called F of xi. So F of xi is the fitness of the type I in a population divided in different types. And the average fitness of the whole population, which is the average over all the classes, it's just called phi over x, because it depends on all classes, not only one. And this simple model, ecological model of called replicator dynamics, says that each of this type probability, the probability of belonging to each of this class I, it's made as such. It's proportional to the probability of being in that class multiplied. So the rate of change, this is the derivative in time, it's proportional to the probability of being in that class. And this is how better your current fitness is respect to the average. F of xi is the fitness of that type. And phi over x is the average fitness. So this is how much is your fitness better than the average one. Okay, so types with large fitness will get exponentially more present than types of smaller fitness. But you can see that this is exactly what we have defined before in our reinforcement learning. Instead of the classes, the types of populations, now we have the probability of doing some action. Okay, so instead of having that the population is divided over I types, then my choices were divided in the probability of doing the different actions I. And the fitness is the expected payoff for that choice. So if I want my fitness of being in a class I is my fitness of doing action I, which is just the sum over all the possible action of the other dude, of the other agent, and the average reward is average over his policy of doing action K. So the sum over all the action of the second agent, of the probability of the second agent to do that, and the reward if I do I and he got K. Okay, so the expected payoff for an action given the strategy of the other is the fitness of that action. And the average fitness is just, okay, it's the same as before, but not only I sum over the possible action of the second agent, but I also sum over action of the first agent. Okay, this is nice because now we have a deep connection between what we've just seen, multi-agent reinforcement learning with natural gradient, which is that two agents learning strategies in matrix games, it's actually the same dynamics of what is a growth model considering a population with fitness which depends on the types. Okay. Also, it's nice because now this model here, it's not a model of natural gradients of expected payoff. This is a model which is a differential equation. So this is a model which can be solved analytically. It's a very simple model, analytically or numerically, but it's a different approach of solution, right? One was, I have two algorithms with X3, they need to store the information and value approximation and X. Here we have just a mathematical equation and you have to solve an ordinary differential equation, which we can do. And Python, fortunately enough, gives already also a very simple library to solve this kind of ordinary differential equations. And it's the same as before. I have the two payoffs. I have to define, so this function of SciPy wants to solve this kind of equation, want to solve respect of the differential, the derivative with respect of time of some vector p, and he wants the function that at each time t takes p and calculates this derivative. So he wants to have a way to calculate this. Okay, this is Python to solve this. It's just a solver. So this payoff here is just a Python way which I used just to create a function payoff which takes the probability of doing the two actions, and then it does everything which is called here. Okay, so it just does the fitness of an action with a matrix multiplication, and it does the fitness of a different action with another matrix multiplication. Then it does the average fitness doing matrix multiplication crossed with, so only this payoff does is just calculate, given the probability, what is the payoff. So it just means that I gave it a way to, if I give it x of p, I gave it a way to calculate these two terms here. This is nothing fancy, it's just technical stuff. And then I can solve this ordinary differential equation one way, precisely, mathematically, and I can compare it to what I found with a natural algorithm. So you see, these are two completely different questions. One is two agents which play, stochastically play different actions and see they pay off and change their policy looking what the other did in that time and following this stochastic way to approach, to better their policies. And the other one is, I have a well-defined ordinary differential equation. I'm going to solve it directly. And now we can, I already did the calculation, and we can try to see what happens in the case which we had before. So before, I lied to you in the sense that I did not discuss the third line. I hope you can see. Here there are three colors. The green and the purple one are those coming from the natural gradient. So these are positions updated each time with our natural gradient algorithm. And this blue curve here is the solution, the mathematical solution with a numerical solution of the differential equation with the same initialization as the purple one. Okay, so you can see that they are exactly the same, apart from a random noise, because of course the purple line, so the one which comes from the simulation, each player have to do the two actions, so it's the signal is stochastic, and in the blue line the signal is just one, because we have one well-defined equation. Okay, this is like, again, the numerical proof that the two things are actually doing the same thing. Okay, just to show that the two are natural gradient multi-agent learning is equivalent to replicator dynamics. And you can see that indeed this gives the same result. So last thing, which we'll discuss, there is another class which is very actually interesting to study, which are called social dilemmas problems, in which there is you can see there is a lot about it. Then there are problems in which the optimal solution, which we would think, is not exactly what it's actually stable. So, for example, there is this very famous prisoner dilemma, and there are two persons taken by the police, and they have two choices: either to accuse the other of the crime, or not talk to the police. And if they both accuse the other, then they both get a lot of years in prison, so 6 years in prison. And if they both do not talk, then the police have no way to incarcerate them for long, so they both get only 1 year in prison. But if one talks and the other no, then the one who talks gets 0. It's free, and the other one gets a lot of years, even more than they both talk. Okay. So it's clear what one normal, it's looking at the table, it's clear that the best case scenario for both is that they both do not speak, okay? But this is a problem, because if they do not speak, they are both inclined, okay, but the other one is not speaking. I don't want to do even 1 year in prison, so I will speak. But then if both speak, they both get 6 years. So this is one instance of a social dilemma. And the interesting thing is that, so what happens if I try to solve it with reinforcement learning, which is equivalent to replicator dynamics, which is the equivalent of the way in which game theory which leads to a stable solution. This is what happens. So the probability, I started randomly in 2 different places. So this is the probability for the first prisoner to talk. This is the probability for the second prisoner to talk. Wherever I start, I end up to this probability 1 for both to talk. So wherever I start, this natural gradient, which is the way these 2 curves are being constructed, they lead both prisoners to talk. So they lead both prisoners to accuse the others. So the stable solution is not the one in which both say, I don't speak to the police and get minimum collective amount of years, but they both speak and they get both 6 years. Okay, just so in this you can do just changing this matrix here. You can have many different actions. You can have just playing with the payoff matrix. You can see what happens to the evolution of the policies in time. One other thing which it's very interesting is that now we have played with deterministic reward. So if I play I and you play J, the result is always the same, but it can be stochastic. So it can be on average, it's some value, but it can fluctuate around the value. And this is perfectly fine with the algorithm. So this way of dealing with the problem does not have any problem with the stochasticity of the reward itself. Okay. And this is rather remarkable because imagine that you are playing football, two teams against each other, and every time one scores, then there is a flip to see who gets the point, okay? So in that case, humans would not have any idea how to play football in which the reward is stochastic whenever the goal is done. But here, it's actually, for the algorithm point of view, the solution is the same. So even if not only the action choices are random, but the payoffs given the actions are stochastic variables, then the algorithm still learns. Okay, so this was just to see that there is a deep connection between natural gradient algorithms in matrix games and the replicator dynamics, so evolutionary game theory. I would stop here. So if we take a small break, if in this break you want to try to install the what is here with Gym, and then try to run your notebook, perhaps you will not find this dem error here, but you will have nice videos to see what environments can do. But we will deal after the break, I'd say at 10:05. Okay, I will pause. Okay, so even if unfortunately, we will not be able to see the videos. This is something which still works nonetheless, and I think it's rather interesting. So we have seen different algorithms. We have seen the basics of the algorithm, how they work, why they work, what they are trying to do. And of course, there is a gap between what we have seen in these exercises before, in these notebooks, and where is the real world, okay? But fortunately, this gap, even if it's huge, it has been bridged by many excellent computer scientists and teachers with so many resources available online for free. So a lot of work has been done, and I will show, done by OpenAI. This is their GitHub repository where you can find a lot of things. And in particular, you can see that there are here the most interesting part are these four here. So Gym is this packet which we unfortunately not always can install, but I'm sure that if you try it for a couple of minutes, you will find solutions online. Gym is a package which contains environments. This is their actual page, so this was the code. And environments means that there are lots of different worlds in which you can navigate, and all these different words have been written in a very similar way, so that, okay, the word is against me today. Okay, perfect. And you can see that there are separated in different sections here. For example, we already seen cart pole. We've played with cart pole, but then we could say, okay, let's try to do this pendulum. We want, given a torque, we want to swing a pendulum. So we have to learn how to do this to make it swing. All of these environments work in the same way, in the sense that they have the same structure and the same way to be called and the same way to be dealt, and all of them are very similar. So if you manage to install Gym, then you create an environment with their name, and then every time that you reset the environment, you get to the starting, they get the starting state, and then every time you want to do a step, you give it an action, and inside the environment there are all the information you need to actually see what is the state space, what is the action space. So they are ready to use the environment with a lot of possibilities, because of course this one are simple, in which the state is continuous, but there is only two actions. But there are much more complex one. For example, you need to try to learn to walk. You need to try to learn how to drive. I mean, this one here, which we will unfortunately not see the videos, but is something which we will see. This is a nice one. You can have 3 action, and you want to land inside the two flanks, and with a small enough vertical velocity, and also perfectly flat. Otherwise, you crash. Okay, so if gives you the opportunity to have very different problems, not only in the complexity range, but also in the different states. For example, I want a continuous continuous state space problem with discrete action. You can find one. I want continuous space, but also continuous action. You can find one. I want a discrete space, but continuous action. So this gives you a lot of very concisely written, efficient way to play around. Also, as students, you can ask permission to install this Mujoko, which is a fast physics simulator in which you can actually try to do essentially almost robotic tasks. I mean, these are just very simple tasks, but these are in a physics engine. It's like real life for this spider-like object and or real robotics. So this is again, you can install it, and then you have an environment which capture the essential physics of the real hand manipulation of an object, of a grabbing time. So this and all of these have the same internal structure in the sense that they can be called and dealt with from outside in a very simple manner. If you go to the actual code, you will see that it's clear in the GitHub repository. It's very complex, but you do not need a lot. But anywhere, all of them have a step function which returns always the same observable reward done and info. They all have a reset button and they all have a render, and all the other things perhaps you don't need to understand. Okay, so they are very modular and they give you a lot of exploration space to play with. And if you want to go very, very simple, very cost light, you can do this. These are called text environments. For example, these are just you have to move in a grid of letters for it to cross a frozen lake or something. Okay, you can play games. Okay. They are all the same basic structure, so it gives you a wide amount of words to explore. Instead of having to create them from scratch, you can find them here and try your algorithm to work on that. So this is a very useful tool, and if when you manage to install, I'm sure you will, because I mean I managed, but my render does not work, but they can work. Okay, and again, also the robotic part, you have to either you get a free trial, but if you're a student, you actually can ask for permission to install, and then you have access to all the robotics environments, which is fun. And this is for environment, so gives you free environments, work very simple to work, very accessed, very documented to work. If I managed to, I would show you. Sometimes it worked, but I'm sure today it will not work. Wait. Yeah, no. Yeah, does not work, but okay. Then this is from the part from the environment part. So this is a tool for you to play and explore. From the algorithms part, also there is a very nice, there are very nice resources online, and I already pointed you towards this once, but I will do it again. This is a second leg of the OpenAI monster, which is called spinning up. Spinning up in the sense that it wants a researcher to get as fast as possible connected to the world of reinforcement learning, and this has a very nice blog, and inside here you can find a lot of things. Okay, first of all, it's on the part of the algorithm, so it presents you with how many? 6 different algorithms which are already created, already coded, and you can use them immediately. But the nice thing is, instead of giving only the algorithm and how to run it, has a lot of information. For each of these algorithms, for example, this is vanilla policy gradient. This is what we already seen as an exercise. And it gives you the theory part, it gives you the documentation part, so how the code is written, how the code works, and it gives you also very relevant papers to study if you have a question, okay, but where does this term come from, where does this come from, and it also has a very nice reference section. So the background is very simple. You can recognize many of the things, and perhaps they have different conventions, but it's very interesting. So we see that this is the gradient of expected payoff, and now we see the nabla log of the probability. Now we use Q. Now this is advantage. Then there is a lot of part on the advantage. There is a lot of information, exploration, exploitation. The nice thing is all of these algorithms. So we have seen them as basic algorithms, so the vanilla policy gradient as a basic thing. These are already constructed in a way that they are interacting with artificial neural networks. Most of the time, the critic, the function approximation is done with artificial neural network, and it's done in a proper way. It's well documented, but it's done in an efficient way. So the nice thing is you have seen the skeleton of these algorithms, perhaps with linear approximation, perhaps with tabular values, and now you can see an implementation which has already artificial neural networks. And again, you can go in the documentation. For example, this is inside OpenAI. You can find this spinning up. Then from the spinning up, you see the spin, when there are the algorithms, and then you can choose one of the two versions. For example, this is the vanilla policy gradient. And then you can try to read the algorithm. Actually, it seems rather cumbersome, but most of it is, first of all, it's a lot of commands. And then it's actually the core of the algorithm is very simple. So let me zoom a bit. So where are the main differences between what we have seen so far and with these algorithms you have seen here? So we have done inline step-by-step update, but what they do is that they collect first a lot of experience and only then they do an update. And this you can see because there is a lot of the code is actually this called vanilla policy gradient buffer, which has a lot of, you see, vector which store observables, store actions, store advantage functions, store rewards, store returns, store values, okay? And indeed they have function which you can give them and they store in memory. So they have a lot of information which actually is just because they, instead of doing step by step, they collect a lot of information and they make an update afterwards. But the true algorithm, it's here, it's in this definition here. And again, has a lot of perfectly written, very well written documentation. So it gives you a lot of what the different variables are, what it's very well written. So this, for example, this is 175 lines of code, and we didn't even get to the it's just something nice. It didn't get to the algorithm. The algorithm actually has only one thing, which is then a lot of things are to the log for logging. So again, not real algorithm. One thing is different. Again, it's that they always use artificial neural networks. So this is already a point further in complexity. But one thing it's rather different. It's conceptually the same, but it's a different way of approach. So right now we generally we calculate the gradient and we do an update moving along the gradient. But generally speaking, artificial networks have their own framework, and it's much more convenient to calculate the loss, and then to calculate the gradient, it's done by the frameworks. What it means? But it means that, generally speaking, we would calculate the gradient of the logarithm, etc., etc. Okay, but what these algorithms do generally is that they let me find if I yes, they generally we calculate already the gradient and apply it, but they store the loss. The loss is what we want to calculate the gradient of. So they store the logarithm of the probabilities multiplied by the advantages of the Q. So they first calculate logarithm multiplied by Q, and then this is the quantity which is given to the neural network, and the neural network by itself has all the tools to calculate the gradient. Okay, this is just to say that don't get confused by this main difference. In our algorithm, usually we already can compute by ourselves the gradient because it was very simple, and we apply to the parameters, etc., etc. All of these algorithms actually compute the loss, so the expected reward which they want to maximize, or minus the expected reward they want to minimize, and this loss is given then automatically to compute by the neural network. But this is just to say that even if it's a bit more complex, it's actually not that hard to skip into the code. But if you do not care about the code, you can go here. Again, in the spinning up part, you go in installation, and in very few lines, you can install the environment for it, and then you have a few packages to install, and then you can install this spinning up system, and then you can actually run their algorithm over the environment we just show in the gym, and it's very easy, and it's as easy as this. Okay, so you have, for example, once you install it and you are in the correct folder, you say, okay, this works with Python. There is already a script to run it, and you say, I'm using this. Here it means that I'm using artificial neural network with hidden layers of size 32, 32. Okay, this is just shorthand. I want to solve the environment of the lunar lander. I will call it this so that I know which folder it's written. I'm using gamma. I'm doing this many steps, these epochs. And here you can play around a lot. You can, of course, this is the name of the algorithm you want to use. So for example, you want to check how with the same amount of data points, what is best? Is it vanilla policy gradient? Is it PPO, or is it something? This is a way which you can produce results, and all the parameters of the algorithm you can check their relative importance, just changing by name when you call it. Okay, this is how easy it is to use them. Of course, then you want to understand then you want to understand how they perform. Generally speaking, you can have ways to render the policy. So this environment, there is a very simple way. It's just the same code, but it's the same script, but you run it in a different way. It produced the video, and yesterday it worked for 5 minutes. Then again, I found the same error. But again, it's a very nice thing, and there is a lot of information you can find here in this install. For example, you can run it, and then you can see this one creates a video of the policy which are at the end. So I was able to see the lunar landing actually landing and not crashing, but I cannot see it anymore. You can, and then you have, once you do that, you have, for example, this was my initial part. So this was my lunar landing, and this was all the information is saved when she learned. And for example, I could see that this was somewhere in the world. Okay, so this, for example, was this was the number of hundreds of tens of thousands of episodes. Okay, and this was the reward of a lunar. Here it crashed all the time, and then as the learning processed, it went in the region of positive rewards. Okay, everything it can be done automatically by the program, but unfortunately I have this problem with rendering images. This just to say that if you want to check out the performance of the algorithm, to check out how these different algorithms perform for a given task, if you want to see how well they in general mix, so there are algorithms which work with discrete actions or with continuous action, etc., etc. Actually, here you have also a well-documented way to access the algorithm and to try them on real life or more complex environments. Okay, then if you want to go super deep into this and you think that your algorithm performs better than the state of the art, then there is another branch, another leg of the OpenAI program, which is called baselines, and they are indeed baselines. So baselines are code that algorithms which they claim they are efficient up to standard. So if you have a different algorithm which say, okay, this is for sure better than the best written vanilla policy gradient, you don't need to write the most efficient vanilla policy gradient yourself, but you can go to OpenAI, you go to baselines, and baselines, where they lack in documentation, they for sure excel in efficiency. So again, if you have a very different problem which you have created, you want to solve it with one which is close to the optimal way of writing a particular algorithm, you can use these baselines. Again, they are A to C, so actor to critic, and they are different one. You can see policy proximal optimization in two different ways, trust region policy approximation, okay, deep Q learning. There's a lot of them. So inside of this OpenAI program, you can find a lot of tools. You can find environments which are simple to use and can give you a huge variety of problems which you want to solve. And you can create your own simple algorithm and approach with the environment, like we did with Carpol. Or you can go and want to study in more detail how efficient but clear representation of reinforcement algorithm work. You can go to spinning up. There is a lot of documentation. There is a lot of documentation if you want to understand, for example, how to apply neural networks with simple framework of coding. And you can mix the two. And then if you think you have reached a level of maturity to go to state of the art, of course, there is this. I apologize. I assure you that it's the best thing of all of this is actually be able to install Gym and to run this and look on your screen where a computer tries to play Space Invaders. But unfortunately, I tried several times yesterday and I could not manage to make the render work. Okay, so I will stop sharing, and then if you have questions.